My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 609. In this lecture, we will try to understand example convolutional neural network, that is LeNet. Let's look at a very popular and simple convolutional neural network called LeNet. It was actually created by Wei LeCun, who is one of the most popular figures. He came up with the whole idea of convolutions in deep networks. This paper was actually published in 1998. Here is a very interesting story. Even though the CNN, the idea was published in Research Fairly and Thoroughly in late 90s, it did not become popular till almost 2012. The reason being, the fundamental reason being, even though some of these ideas were present there, we did not have large data sets or GPUs for that matter. Remember, the whole popularity of deep learning, some of these concepts are almost they have been there since 1998 itself, isn't it? But why did it take almost 15 years? These techniques to take 15 years. These techniques to become popular. Even the theory behind some of these concepts are already present. It because we did not have large data sets to train deep neural networks. To train deep, we did not have large data sets to train deep neural networks. Similarly, we did not have GPUs. Lots of compute power was required. And remember, in late 1998, lot of people lost faith. Lot of people lost faith in neural network because neural network did not work very well, because of the failure of neural network. Even though they become popular in late 1980s, by the time late 90s, the more popular algorithms were support vector missions, SVMs, and tons of research work on SVMs. Because SVMs were so popular, everybody took notice of SVMs, but really don't care about LeNet. There were only small group of researchers. There are only small group of researchers like Wei LeCun, Jeff Hinton, etc., who struggled to publish research work in late 90s because people said, does it really matters anymore? They actually came in 2012. In research, what happens is you may have the most brilliant idea, but the timing is not right, and unfortunately, because you don't have large data sets and GPUs, you have not been able to prove full potential of your algorithms. This is happened to some of the most brilliant minds in computer science, for that matter, even machine learning. And Wei LeCun is Wei LeCun, I can say. Wei LeCun is one such guy. This is just observe this one. This is one architecture of LeNet. There are multiple slight differentiated architectures, but I will explain this. The input image. What is my input image? Input image size is 32 by 32 grayscale image. Remember, this was in late 90s. We don't have computational power, so people even did not think of color images and RGB images at all. They think of small images. The task, what is the task here? The task that they're looking at was they were looking at MNIST task, detecting handwritten characters, and the architecture is very, very interesting. The first layer is convolutional. They called, just see what is first layer. First layer is called convolutional. They called feature maps here. Feature maps basically what is the meaning of feature maps? Feature maps basically called kernels, isn't it? Feature maps and kernel both are for same meaning. And C here, what is my C? Yes, feature maps and feature maps, what it says, feature maps basically called kernel. C is, what is my C here says that it is convolutional layer. And we have how many kernels we have here? We have 6 kernels here, and the output size is, what is the output size? My output size is 28 by 28. What is my kernel size? The kernel size is 5 cross 5. They don't have padding and all of those concepts. Here it says the kernel size. What is my kernel size? My kernel size is 5 cross 5, and the activation unit, what is my activation unit? Activation unit is sigmoid unit. Remember, in 1998 they did not have activation units like ReLUs, isn't it? So the kernel they are using is 5 cross 5, and the image is grayscale image, isn't it? And we have how many kernels? We have 6 kernels here. How many such kernels? There are 6 kernels. Each kernel size is 5 by 5. So this tensor, so the tensor is of size 28 cross, what will I get? I will get tensor is of size 28 cross 28 into 6. If you have 5 by 5 kernel and you have 6 kernels, just see, if you have 5 by 5 kernels and you have, what is my kernel size? 5 by 5 means k cross k, isn't it? What is my input image size? N cross n. What is my n here? Just observe here. Just we already learned this one. N cross n. Your n value is 32. Your kernel size is k cross k. K equal to 5. What is output image size? N minus k plus 1. This I already discussed few lectures back. My n is 32. My k is 5. 32 minus 5 plus 1. I will get 28. That size of the image. Just see what is the image size. Output image size is here. You are getting 28 by 28, isn't it? The 28. That's the size of output image. So first layer is, what is my first layer? First layer is convolution. Second layer is called it as subsampling, isn't it? Remember, the activation units here are sigmoid, and they are not ReLU, because ReLU was not invented by 1998. Today we don't use sigmoids anymore. We use ReLUs only, isn't it? The second stage is called subsampling, which is nothing but you mean pooling literally. Subsampling in the means, what is the meaning of subsampling? Which means mean pooling, isn't it? What do we do in mean pooling? We take 4 pixels, for example, we take 4 pixels and we take the average, of them and generate 1 pixel here. That's what we do in mean pooling. Each of this image 28 by 28, isn't it? What is the image size? 28 by 28. They do mean pooling with a pool of size 2. See, even 2 by 2, so every 2 by 2 will become 1 by 1. That's why, because it's a pool size 2. Your 2 by 2 will become, you will take average of the 2 by 2 means 4 pixels, you will replace by 1, isn't it? So every 2 by 2 will become 1 by 1 here. So now what we have here is the tensor, which is of size. Now you will get 14 by 14. 14 by 14. What is the reason? Why? Because you are taking mean sampling. Just see here, 28 by 28, you are getting 14 by 14. Why? Because every 2 by 2 pixel is converted into 1 by 1. So that's what happening. It's converting like this. 628 by 20. 6. How many? What is that? 6. We are saying that how many kernels? There are 6 kernels. Each kernel size is 5 by 5. Again, what you are doing? Again, convolution, subsampling, isn't it? Same procedure we have. Subsampling is nothing but average pooling. Your input image size now 14 by 14. Number of kernels are 6. Output image size is n minus k plus 1. Same procedure. Your kernel is here. Just see. Your kernel is, what is this kernel? Your kernel is 5 cross 5. isn't it? Your input image size 14 by 4, n minus k plus 1, you will get 10 by 10. Just see, you are getting what you are getting. You are getting 10 by 10. Just it's a similar procedure. Actually, if you keep on continuing this procedure, just observe this procedure carefully. What happens? So actually, what is the task here? You have to detect the digit. That's what is the task here? MNIST task, isn't it? What is the MNIST task here? If you observe carefully, let's look at again this. This is my input image. Just let me explain this one again. This is my input image. I do convolution. I do subsampling, means mean sampling. Again convolution. Again mean sampling. Mean sampling means subsampling, isn't it? Then what you are doing here, what I do FC layer. FC means fully connected, isn't it? My output layer, which is my softmax, isn't it? And the task here, because it has 10 units, just say output, you have 10 units. You are trying to detect whether it is 0, 1, 2, so on 9. It is a 10 class classifier. MNIST, this was fairly big deal in those days. This is MNIST task. It's 1998. It's a fairly big deal, isn't it? How many layers we have? We have. It is not very deep network. If you observe carefully, it is not very deep network, but it works very well in the late 1990s for simple tasks like MNIST, means detecting digits. We have learned about convolution. We learn about mean pooling. This is a whole structure. This is just, if you observe, this is the whole structure of LANet. Slightly old network, but still powerful, good network to learn. I recommend you to go through various blocks on this particular LANet so that you can understand. Each of the layers are very neatly explained, like what is the kernel size, what is the activation. And I would like to show you few blocks. I request all of you to refer few blocks. For example, just see here let me show. This is one block, LANet 5 architecture explained. Just how neatly they are explaining. Just see. Just I request all of you, just see. This is the image on which we worked. Just I request all of you to go through blogs related to this particular convolutional neural network, that is LANet. There is another blog, just see, LANet 5, a classic CNN architecture. It's a classic convolutional neural network. Just see, it's a classic convolutional neural network. Just go through various blogs related to LANet so that you can understand. If you have any difficulty, please keep a comment. Thank you very much.